Welcome to Edexcel Further Pure, Complex Numbers 1, an Introduction to Complex Numbers. In this first session we're going to solve some quadratic equations and look at those quadratic equations with no real roots. As a reminder, we will solve x squared minus 5x plus 6 equals 0. This will factorise as x minus 2 times x minus 3 equals 0. And it has the roots x equals 2 or x equals 3. So it has two distinct real roots. So far your quadratic equations have always had two real roots or a repeated root. For example, x minus 5 squared equals 0 has the repeated root x equals 5. If we look at this second quadratic equation, x squared minus 4x minus 13 equals 0, I'm going to solve this one by completing the square. X minus 2 squared. Minus 2 squared is 4, so I've got to take off 4 before I take off the 13. And then rearranging, x minus 2 squared is 17. Don't forget when you square root both sides that you'll get two square roots of root 17, and x is 2 plus or minus root 17. So in this example, the discriminant of the quadratic equation was 68, which is greater than 0, so we would expect two distinct real roots, and this equation has two real roots which just happen to be irrational. However, mathematicians wanted all quadratic equations to have two roots, some of which will now be a pair of complex numbers. So let's have a look at a quadratic equation with no real roots. We're going to solve x squared minus 4x plus 13 equals 0. Again, I'm going to complete the square, so it's x minus 2 all squared. Minus 2 squared is 4, so we take off 4 before adding on the 13. Rearranging, x minus 2 squared is minus 9. And square rooting both sides, get two square roots again, plus or minus the square root of minus 9. X equals 2 plus or minus. The square root of minus 9 can be written as the square root of 9 times the square root of minus 1 using my laws of indices. So now we have a quadratic equation where the discriminant was minus 36, which is a negative number, so we would expect non-real roots. We've got x equals 2 plus or minus root 9 times root minus 1. This solution can be expressed by introducing another category of number called imaginary. These are based on the fundamental idea that the square root of minus 1 does exist and is represented by square root of minus 1 equals I. X equals 2 plus or minus 3i are the roots of this quadratic equation. So the equation has two roots. These roots are complex. For example, the root 2 plus 3i is a complex number. 2 is the real part of this number. 3i is the imaginary part of this number. So let's have a look at an exam style problem. We've got to find the solutions to the equation z squared minus 10z plus 28 equals 0, and these are the roots z1 and z2. And we need to find these roots in the form p plus or minus I root q, where p and q are integers. Notice it's often desirable to use z as a variable in complex numbers. So we're going to solve z squared minus 10z plus 28 equals 0. Again, I'm going to complete the square. Z minus 5 squared. Minus 5 squared is 25, so I take off the 25 before adding on the 28. Z minus 5 squared is minus 3. carefully square rooting both sides. I get plus or minus the square root of minus 3. Therefore z is 5 plus or minus the square root of 3 times the square root of minus 1. Therefore z is 5 plus or minus root 3i. So our two roots are z1 equals 5 plus root 3i and z2 equals 5 minus root 3i. It doesn't matter which one is defined as z1 or z2. In our next session, we're going to be looking at adding and subtracting complex numbers.